Hi everybody. In this video, we're going to discuss the use of symbolic data in Matlab. Now, as you know, the core of Matlab is the use of matrices. And basically, the essence of Matlab is using linear algebra and numerical techniques. So Matlab, for the most part, uses numerical data in their computations. Okay. But it includes an additional toolbox, which is a symbolic toolbox, which uses symbolic computations, slightly different from numerical computations. So it allows us, for example, to solve symbolically to find some solution to a differential equation, as we're going to solve it today, but not an actual numerical solution. Okay, a symbolic solution, pretty much like how we would solve a differential equation by hand. Okay, it also involves some other commands like plotting symbolic data. So let's see everything. I'm going to show you the most common commands of the symbolic toolbox, which you can use to solve algebraic equations, differential equations, or to plot data. Okay, so just a couple of commands we are going to see today. Now, you need the symbolic toolbox to work for this type of commands. The first command that we're going to see has to do with plotting data. It's fplot, and I give you here the very small explanation. Basically, with fplot, what we can do is call upon a function by defining the function's free variable. Okay, we can actually give a range, but the default range is -5 to 5. So let's see this command right here. It's fplot at t, which means that we are calling a symbolic function that uses the variable t to define the shape of the function, okay? And I'm using here sine of t squared plus 1. Then using hold all, I have another function, which is fplot at x cosine x to the third plus 1. And then I have another function, f at x, sine of x plus cosine of x. So you can see I can actually change this symbol. I can see, for example, uh, at w, of course, I need to change the shape, the form of the function, sine w plus cosine w. And if I plot all of these, I basically get the shape for these functions. And with fplot, I can use all the classic commands that I use in the classic plot. So here I change red, green, and blue color for the curves. Okay, so this is a simpler form of the fplot command. But what we can do is actually have sort of different formula for the function that we're using, and we can do so using f-implicit. Now, f-implicit plots actually a function that is that is defined through an implicit formula. An implicit formula has this sort of form. So we are using two free parameters here, x and y, inside some expression f, which is equal to 0. But how we do that? Again, it has some default values for x and y that we can change, but the default value is -5 to 5. And here is the formula. Okay, let me make it a little bit bigger. So here I'm calling f implicit at x and y. So our free variables are x and y. And the expression that I have is basically the expression of a circle, x squared plus x squared minus 1. Okay, basically the expression that I'm using here is x squared plus y squared equals 1, right? Which is the expression of a circle. But in f implicit, I'm not going to define it this way. I'm going to define it by moving all of the terms to the left-hand side, and MATLAB assumes that the right-hand side is equal to 0. So we need to first, using pen and paper, or maybe using some other command, we need to derive the expression in this implicit form. Some expression of x and y is equal to 0. So basically the expression for the circle x squared plus x squared equals 1. If I write it in this form is x squared plus y squared minus 1. Okay, I don't have to write equal 0 or equal 0 with double equal sign. Okay, MATLAB assumes that the expression that I'm using is going to be solved for equals 0 on the right hand side. Okay, so here I have the expression of a circle, and then the other expressions I think are some parabola or whatever. Let's plot everything. So here we have x minus 1 squared plus y squared equals 1. So we move equals 1 to the right side, to the left side, I'm sorry, and it becomes -1. And similarly, this is supposed to be equal 0. This is supposed to be equal 0. Okay, very nice. And we get all of these graphs. You can improve, of course, upon the graph by changing the width, changing the labels, adding legends, changing the text size, whatever you like. Okay, so these are the basic plotting commands. And obviously, for these plotting commands, you can use outside variables. So here, for example, I have a for loop. For c equals 1 up to 10, I call f implicit for x and y, which are the free variables, and I have this parameter c right here, so I'm gonna get different variations of this graph right here. Okay, so everything that you know that works from the classic plot command, you can actually use it here as well. Okay, now, these are all the basics for plotting. Let's move to the most important part, and actually the most interesting part, solving linear systems. Oh no, not linear, sorry, non-linear as well. So the classic command that we can use is solve, which can solve either one specific equation or a collection of equations. Okay, linear or non-linear. Okay. The first thing we have to do though is define some variables as symbolic variables. Now, as you know, if I'm trying to have some operations like x times 10, there is an error here because actually I haven't given any value to the parameter, to the variable x. Okay, I need to use some numerical value like x equals 1 and then do the operation x times 10. Okay, with symbolic data though, this is different because I can define some symbolic value, some symbolic variable like x. Okay, and now x doesn't have a specific value. It is actually a variable that has symbolic nature. So I can write x times 10 and I get the result, which is again a symbolic result, which is basically by Matlab an expression that is times 10 times some variable x. Okay, so we can build upon this and use some expressions to define algebraic equations and then solve these algebraic equations. So let me give you an example. Here I have this line that defines s, c1 and c2, which are three symbolic variables, and then I can call upon solve to find the solution of a polynomial. So here I have a polynomial s squared plus 2s plus 1 equals 0. Now remember, this is a logical expression. So in logical expressions, I cannot use a simple equal sign because if you remember from other programming languages, or from other videos on Matlab as well, this simple equal sign is used only to assign a value. Here we will need a symbolic expression, a logical expression, so we need to check whether the left-hand side is equal to the right-hand side. So if I run this, I get the solution. Oops, I'm sorry. Let me also define the symbolic values. So I get the solution, which is a polynomial expression. It has a double root to -1. Right. I can actually use this and build upon this to solve systems of equations. So here I have a system of two different algebraic equations, 2 times c1 plus 3 times c2 equals 0, comma, and this is the second equation. So if I'm going to use a system of many equations, I simply separate them using commas. Okay, so let's solve this and assign the value of the solve to a variable solve. Okay, you see that I'm getting not an exactly double value result. I'm getting a structure as a result. Okay, this is the output of the solve function, which tells us that C1 is -3 over 16, C2 is 1 over 8. Okay, I can obtain, let me see, if I simply plot solve, I'm getting this structure. So if I'm having, let's say, a very large algorithm or some script that I'm going to use C1 and C2, how I'm going to use them? I simply say solve.c1 and then I obtain the value of -3 divided by 16. If I plot solve.c2, I'm getting the solution for the parameter c2. Okay, I can use also double for solve.c1 and it simply transforms the symbolic expression -3 over 16 to a double expression floating point. Okay, so these are different results in case you're gonna use the solution of a solve into another part of an algorithm. Let's say you are designing a controller in control systems or some other part in numerical analysis or whatever. You may need to do this transformation. Okay, just keep it in mind. So solve works very easily whether you have a single equation or multiple equations. Now, let's move on to solving differential equations. Much more interesting topic. Again, we need to define our symbolic variables. Now, there are many different ways in which the dsolve works. What I like to do is define the independent variable, let's say time, as t, and then uh, define our variable in the differential equation as y of t. Okay. Now, this is not mandatory. I can simply define s syms t and y as it is, but when writing code, I find it better writing it this way because it can work both ways, but it helps me better when I'm structuring a differential equation so that I don't make any mistakes. Uh, Choose what you want. You can actually experiment a lot in your own computer. So I'm defining, um, I'm sorry, let me write this down here because I want this to be visible. Okay, and now let us define a differential equation. Now the differential equation I want to define is the derivative of y is equal y. First order linear differential equation. How am I going to do that? Well, I need to define y derivative. Okay, so y derivative, the best way to define it is using the function diff. Okay, now to solve a differential equation, I simply write dsolve. It's slightly different than the classic solve. It's dsolve, and inside here we structure the differential equation. So my differential equation is derivative of y is equal to y, and this is what I write. The right part is double equal sign y of t. Okay, and the derivative is defined through the function diff. Okay, so diff here is a function that can be used to define the derivative of an expression. Okay, so I can simply write der1 equal diff of yt, and this simply tells us that der1 is now the derivative of the function y of t with respect to t. Okay, this is understandable. If I write uh, diff2, can you guess what this does? This defines the second order derivative of the function y. Okay, and again, these are all symbolic representations. Okay, I can try something else. For example, try diff of t squared, and it computes the derivative of t squared, okay, which is a polynomial, so it's 2 times t. So you can play around with the derivative. You can either use it an exact argument and it will compute its derivative like t squared, or you can give it a symbolic value like y of t, and it understands that this variable is actually the derivative of your argument. Now here I don't need to define der1. I can simply say the derivative of y should be equal to y. And let's see what the result is. Now, as you know, when solving differential equations, you usually get the result through, which is described through a free variable. And again, here I obtain the solution, and the solution is c1 times exponential of t. Now, if you remember the very basics of a differential equation, this is actually the solution for this differential equation. A free parameter times the exponential of t. Very nice. Now, how can we deal with C1? Two ways. Here we solve the differential equation without initial conditions, and this is why the solution has a free variable. What we could do is take this solution and replace this free variable with a variable that we like, with a value that we like. So here I do this thing. I have this dsolve. I solve the differential equation. Okay, and then I have another line which is specific solve, which is the specific solution, and I use another function which is subs from substitution. So I tell it, after you obtain the solution of dsolve, let's write it down again. Okay, this is the expression. What can you do? You take the solution, okay, and substitute C1, and look at this detail right here. I give C1 here as a string. Okay, if I give it simply like that, it doesn't understand it. It needs to understand that C1 is a string, and you need to replace this string C1 with 10. So if I do that, I get this specific solution, which is 10 times the exponential of t. Right. Here I'm not solving an initial value problem. I'm simply replacing specific variable okay, a specific parameter, I should say more correctly, with a value that I like. And then I can actually use fplot to plot the specific solution. Okay, so let's see right here. And I actually get the plot of the function, which is of course an unstable function. By the way, see a little detail. As you know, Matlab has different ways of plotting functions. So take a look at that. See how different these two calls to the function are. Here I call with a specific function structure with, initializing at the parameter that I have. Here that I have already defined a specific solution as a function, which is a symbolic expression, I call it and I define the interval of interest. So as you know, this is very common, of course. The way that we can call MATLAB functions differentiates or has many different options. Okay. Now, this has to do with, replacing a specific parameter with a value that I like. If I want to solve initial condition problems in differential equations, I actually call and define the initial condition inside the dsolve function. Okay, so let's see right here. The expression that I have here is dsolve, where here on this part I have the exact same differential equation as before, okay, comma, and then I include the initial condition, which is y0 is equal to 2. Okay, very, very nice. So I call upon this differential equation, and I also tell MATLAB that the initial condition should be equal to 0. So, not to 0, sorry, should be equal to 2. If I solve that, I will obtain a solution that doesn't have a parameter. Okay, why is that? Well, obviously, because I initially obtained the solution with a parameter, and then I replace the initial condition, y0 equals 2, to find the value of the free parameter. So the free parameter here, C1, is equal to 2. Okay, very nice. And then again, I can call upon fplot to obtain the specific solution, which is again an unstable solution. Very, very nice. Okay, so solving a first order differential equation, easy to do. Solving a first order differential equation with initial conditions, again, this is very easy to do. Solving a second order differential equation, well, let's see. Again, this is something very easy to do. Here I have this differential equation. Let me plot it. Let me write it down right here. We have the second derivative of y plus y equals 0. So I showed you earlier. I use dsolve equals 0, the right hand side, and the left hand side is y of t, okay? And the second derivative is defined just like that. We again use the function diff of y, but here we have a second argument which denotes the second derivative of y. So if I run this, I obtain this solution right here. As you remember, second order differential equation, when it is solved, it has two free parameters. So this is the solution here, C1 times cosine minus C2 times sine. Okay, very, very nice. So I obtain, again, two free parameters in my solution. Again, I can use a substitute function in order to replace C1 and C2 with my own values, in case I want to plot the solution through a for loop or whatever. So here I have the same differential equation. I have specific solution is equal to substitute solution. See right here, I give the two variables, okay, but I use brackets. I think that's how they are called in English, these symbols right here. And then I have C1, comma, C2 as strings, and I replace them with the values 1 and 2, which are given in a matrix. So here you see a little bit different when I call the strings and when I call the values that should replace the strings. So here I replace the values with 1 and 2. As you can see right here, cosine has a multiplication of 1 and sine has a multiplication of 2. Okay, and then I obtain the solution. But of course, this is not the same as solving a differential equation for specific initial conditions. So let's come right here towards our last problem for the day and solve this differential equation the same as before, but for specific initial conditions. So let me also use this symbolic right here. So we have the same differential equation as before. The second derivative plus y is equal to 0. And I want to solve for these specific initial conditions. Y0 equals 1, okay, and y dot 0 is also equal to 1. Okay. Now, someone might think, let's try something like that. Let's see why this is not correct. Let me comment on this a bit. So this is a naive approach, and let's see why it gives you an empty solution. What I wrote is this. Uh, dsolve, okay, this is the initial differential equation, comma, y of 0 is equal to 1, which is the first initial condition, and the second initial condition should be the derivative of y at 0 should be equal to 1. Okay, so I write diff of y0. Okay, so the derivative of y0 should be equal to 1. Well, the problem, I don't know if you can understand it, is that here I have made a very big mistake. Simple but big mistake. This expression, okay, is not the derivative of yt. This is basically the derivative of y at time 0 after I replace the time with the value of 0. So basically, I'm differentiating the y of 0, but y of 0 is a stable value. Okay, it's not dependent on time because I have replaced the value of time. So this result is always 0. It's basically the same as differentiating this value. Okay, it's a 0 value. Okay, 1 or 2 or whatever. Um, so Matlab doesn't understand that. Okay, so what do we do here? How can I define initial conditions, not just for y, but for y derivative, uh, first, second, or whatever? Well, I can simply add an additional step, which is that I define the derivative of y in a separate variable. Okay. So now what I did is I define a new variable, yes, variable, which is derivative 1, der1, which is the derivative of y. So now MATLAB understands this as a function, which is the derivative of y. So now I call upon the differential equation and dsolve, this is the differential equation, and I have y of 0 equals 1 and der1 of 0 equals 1. So MATLAB here understands that the function of the derivative at time 0 is equal to 1. Okay, this is different from what we actually had in the beginning where we differentiated a stable value. Okay, this is not differentiation of a stable value. This is the derivative of y at time 0. And then if I run this, I'm going to obtain the actual solution, which doesn't involve any free variables, any free parameters, I'm sorry, because I have given MATLAB two initial conditions. Okay, and of course I can plot this very nicely. Okay, of course, if I only give one initial condition, I'm gonna get a solution that depends on, if you remember the theory, on just one free variable. So then I get the solution cosine t minus c1 times the sine of t. Okay, this is just a side note. So this is how I'm using symbolic data to solve algebraic equations or differential equations. And of course, you can move along and define systems of differential equations. You can try it out for yourself. So the problem structuring is very, very simple. You just need to properly define initial conditions. I think this is only the difficult part where mistakes happen. Properly defining initial conditions for y and its derivatives. Okay, so try it out yourselves. I hope